Okay, write that down, then we're going to explain. I promise it will make sense. What's going on here? What does this all mean? So can I erase this? Let me know if I cannot erase this. Everybody okay if I erase this? All right. If I have a single bond, it's automatically just sigma. So for example, if I draw Cl2, when you have a single bond, automatically the first bond is always a sigma bond. Okay, if electrons can be shared between the two atoms, they're going to do it. So these two electrons are going back and forth, directly back and forth between the two fluorines. That's what makes it a sigma bond. The first choice for a molecule is always to share the electrons in the internuclear space and form a sigma bond. But here's the problem. What if we have a double or triple bond? Where do the other electrons get shared? For example, I got to share 4 electrons between these two oxygens in O2. Now, the first bond is always going to be sigma, but the second is going to be pi. Let's talk about why. 2 of the electrons are going to get shared back and forth between the two atoms in the internuclear space, making that sigma bond. But this space is now taken up. So where do these 2 electrons get shared? They actually get shared above and below the internuclear space. A pi bond actually utilizes atomic p orbitals on the two atoms. The p orbitals are shaped like dumbbells, and it uses those p orbitals to share the electrons above and below the internuclear space. I know, that's crazy. I know what you're saying. What about a triple bond? Awesome question. So if we have N2, double O, the first bond is a sigma bond, but everything else is pi. So there's 2 pi bonds. Here's what this would look like. This gets trippy, folks. The first 2 electrons in the sigma get shared back and forth between the two atoms like that. The next pi is going to be a py orbital, where they share the electrons above and below the internuclear space. So that's that guy. But what about the second pi bond? How does that work? They're going to use the pz orbital. So there's a p orbital coming out at you and going away from you. And the nitrogens are going to share the electrons in front of the board and behind the board like that. It's crazy town, right? In summary, first bond, sigma. Any other bond, if it's double or triple, the remaining bonds have to be pi. Because once you form that sigma bond, once you share 2 electrons between the atoms, that space is occupied. You got to find other space to share the electrons. This, folks, is why there is no quadruple bond, right? We only got 3 dimensions to work with. So we're going to share in the internuclear space, that's the x-axis. We're going to share above and below, that's the y, and we're going to share behind and in front, that's the z-axis. That's why it's all, after a triple bond, it's all used up. There's nothing left. So sigma versus pi bonding, sigma bonding in the internuclear space, pi bonding above and below, in front of, behind the internuclear space. Craziness. I know. Now, pi bonds. Let's write this down. Pi bonds. Use an atomic p orbital. So this gets into something called hybridization. If a molecule like CH4, which is tetrahedral, bond angle of 109.5, if a central atom, like carbon in this case, is making all sigma bonds or using lone pairs. So another example, the trigonal pyramid nitrogen, the bent water. If a molecule has no pi bonds, so these guys have no pi bonds. If a molecule has no pi bonds, then that central atom is going to be what's called sp3 hybridized. sp3 hybridized. sp3 hybridized. I'll explain what that means. So sp3 hybridization means no pi bonds on that atom. Here's what this is saying. If we think about carbon, carbon is in period 2, and it's using a 2s and the 2p's. So it's got the 2s and the 3 2p's. Okay, if you are not making a pi bond, all of your p orbitals are being used to make what are called hybridized bonds, and that's where this sp3 comes from. We use an s and the 3 p's, sp3, right? That's where that comes from. So none of the atomic p orbitals had to be used to make a pi bond, so you have all of them, it's sp3. Now, if you have one pi bond, then that central atom is going to be sp2 hybridized. So for example, if we do COH2, hopefully you can see how this carbon is making 3 sigma bonds. That's a sigma, that's a sigma, one of those is sigma, but one of them is going to be pi. For every pi bond that you are making, you take away an atomic p. So instead of being sp3, take away one of those p's, it's sp2 hybridized. Now, what if you're making, so this is for one pi bond. If you have one pi bond, you are sp2 hybridized. But what if you're making 2 pi bonds? Something like, well, we just did CO2. That should be fresh in your minds. This carbon has got a sigma bond here. First bond between two atoms is always sigma. It's got a sigma bond here. First bond between two atoms is always sigma. But that's a pi, and that's a pi. So what does that mean? Well, if you've got an s and 3 p orbitals that can be used to make bonds, but I need to take 2 of the p's away, it's now just sp hybridized. That central carbon atom is sp hybridized. So you can kind of take a shortcut. You don't really even need to know the theory, right? If everything is a sigma bond, you're sp3. If you have one pi bond, if it's a double bond, right? Okay, then you're sp2. And if you have a triple bond or two double bonds, right? If you're making two pi bonds, then you're sp hybridized. So let me draw just kind of, I'm going to make up a crazy structure that probably doesn't even exist. And we're going to identify the hybridization for the atoms in the structure. So if we look at this structure, go ahead and write that down. So first of all, hydrogen does not hybridize. Hydrogen, since it follows the duet rule, just uses its atomic 1s. It doesn't hybridize, but everybody else does. So we're going to assign the hybridization of that oxygen, that carbon, that oxygen, that carbon, and that nitrogen. That's pretty easy. If you are not making any double or triple bonds, if you are all just bonds in lone pairs, then you're sp3 hybridized. So this oxygen's making one pi bond. That makes it sp2, take away a p. This carbon's making one pi bond. That makes it sp2, take away a p. That carbon is not making any pi bonds. That's 4 sigma bonds. Okay, so that's sp3. This carbon's making 2 pi bonds. That's sp. And that nitrogen's making 2 pi bonds. That's sp. There you go. So you can totally take a shortcut. You don't need to really understand the theory, okay? But just count up the pi bonds. For every pi bond you have, take away an electron, or I'm sorry, take away a p orbital. Yeah, it's like a super awesome shortcut. So that, ladies and gentlemen, I'm pretty darn sure finishes the molecular geometry unit. So